Thousands of years before NIST and the rest of the world agreed on length standards for the graduations on this tape, ancient civilizations were creating their own methods for measuring distance. In the Fertile Crescent, as early as 5000 BC, the Sumerians created the first units of length based on human anatomy. The distance from the elbow to the fingertips was called a cube and is still known today as the cubit. The ancient Egyptians borrowed the cubit from the Sumerians.
Thousands and thousands of workers who built the pyramids were able to take transfers from this master cubit and do the design and the construction of the pyramid. And in fact, the pyramid was built within an accuracy of 0.05% using these wooden sticks that were calibrated off of the master royal granite cubit. The calibration, in fact, was required to take place once every moon under penalty of death. We have somewhat less stringent requirements for recalibration intervals now.
Ancient scribes and engineers all over the world use the human figure measurements. We get our inch from an Old English measurement, the width of a man's thumb at the base of the nail. We actually get our foot from the length of a man's foot. Our yard could have been the length of a man's nose to his fingertips. And our mile, or mille passum, was devised by the Romans and literally translated to 1,000 paces. In reality, the variations among these measurements were vast, but they still led to cultural advancement and expanded trade. Empires had to agree on how to measure their goods in order to price them in a marketplace with ever-growing borders.
But today, the comparability community, if you will, is now worldwide. And so these local standards don't do us any good anymore. We need globally accepted standards.
And that takes us back to Stanley and its strict adherence to NIST standards. If the tape rule sample is good, workers load the rolls into machines that glue on a protective mylar film. Machines then cut the rolls into 250 individual measuring tapes. Each tape is inspected before assembly to weed out any physical abnormalities that would affect its ability to take an accurate measurement.
If they find an anomaly, not only do they select that blade out for scrap, but they also determine the root cause so we can correct that problem. It involves some 87 different attributes that they look for.
Workers move approved blades onto the assembly line, where they're hooked to their springs, encased, screwed tight, and packaged for shipment. Stanley may turn out a high-precision tape rule, but it's only good for measuring relatively short distances. How do you measure the distance around something really big? Or to something really far away? Surveyors have used triangulation since the 6th century BC to measure the heights of mountains and sea islands in order to make better maps. First, they find the distance to the mountain by measuring angles to it from locations at either end of a fixed baseline. Then they use a known altitude to find the angle to the top of the mountain. With that angle, they can calculate the mountain's height. Over 2,000 years ago, Eratosthenes cleverly used triangulation to measure the circumference of the Earth. His calculation was off by less than 1%. And even today, astronomers use triangulation to measure a star's distance from the Earth. Since stars are so far away, their distance is measured in light years. The distance light speeding at 186,000 miles a second travels in 1 year. So we can measure the distance to a star because we can measure time. And we get that essential time measurement from the most accurate clock on Earth. But why does the world need a clock 100 million times more accurate than the one on your wrist? In the 1960s, NIST moved from Washington, D.C. to Gaithersburg, Maryland, in part because the vibrations from city traffic were strong enough to affect the organization's ability to take proper measurements. Measure It will return on Modern Marvels